So let us consider this famous equation in mathematics called the heat equation or the diffusion equation. By the way, with very small changes in alpha, this can also be the quantum mechanical Schrodinger's equation. But in this course, I'll treat it as the heat equation. It's also used in statistical mechanics and condensed matter physics as the Fokker-Planck equation, and in economics, the Black-Scholes equation. So it's very universally, it appears everywhere. It's universally present in many fields. Basically, you have a situation where you could have a steady state, except that there's a flow, either a flow of money or a flow of probability. If you're talking about quantum mechanics, a probability current that feeds into or out of a neighborhood. Or if you're talking about a heat equation, you take a plate and it's got a certain temperature profile, but you decide to heat it up or you cool it down. So you either add heat to the system or subtract heat from the system. So these sorts of processes are governed by this equation. So we follow the usual formula for getting something out of it. Let's first write this as a product decomposition of something that depends only on the space variables and something that depends on just the time variable. That's always a useful thing to do. Then separating variables as usual, when I take the second derivative, I'm going to get phi xx times t equals 1 over alpha squared, and here I'll just get phi times t prime. Now I'm going to divide both of these by little phi times capital T. That's the process known as separation of variables. Then the t's cancel out, and here the phi's cancel out. So I have something that depends only on, well, I guess I should have been a little more careful here. It's phi xx plus phi yy plus phi zz, so I'll call it phi ii. So that's phi xx plus phi yy plus phi zz. That's really what's happening there, because this is just remember always that del squared is del x squared plus del y squared plus del z squared, the Laplacian operator. So that's going to be the Einstein summation convention. All right. Or I could have been a little less coy about this and simply called this a Laplacian. So this is going to be the Laplacian squared of phi over phi. I mean, just a Laplacian. Laplacian, I shouldn't say Laplacian squared, just Laplacian, is equal to 1 over alpha squared times t prime over t. Now, by the usual procedure of separation of variables, each of these things must be equal to either a positive constant or a negative constant. And we'll call that constant k squared, so we are assured that it can only be either positive or either a negative. Now, what can we choose? In quantum mechanics, you have to have the space part to be periodic. So you need to have plus k squared in quantum mechanics. Otherwise, your alpha squared will end up being positive. So you need to have, for alpha squared to end up being negative, you need to choose the plus k squared in quantum mechanics. For because alpha squared in quantum mechanics itself is negative. But in heat equation, alpha squared is positive. So there you have to choose the negative k squared. In either case, I'm not too concerned about the time aspect, what happens here. For it have one thing in quantum mechanics and another thing in the heat equation, and we'll investigate them later. So whatever we do, our time as a function of time will end up being c times e to the minus k squared alpha squared t. Now for the heat equation, you end up choosing the negative k squared because you don't want the object to get infinitely hot. That never happens due to the second law of thermodynamics. So this is, for example, what you would do in the heat equation case. Now, whatever you do for the time part, it's not too important. Let's look at what happens when you have the steady state. The space equation part is known as the steady state part. So let's see what that gives us. The variable k, the constant k that you have, is now intimately wedded to whatever else is going to happen here. So I'm going to get del squared phi over phi is equal to minus k squared for the in case of the heat equation. And so if I multiply both sides by phi, I'll get del squared phi. And if it's not the quantum mechanical case, it's plus or minus. So I'll just put plus or minus there. So del squared phi plus or minus k squared phi equal to 0 is the equation I get. This is a very famous eigenvalue problem in mathematical physics. Why is it an eigenvalue problem? Well, anything is eigenvalue problem if you have operator times function equals constant times function. And that exactly answers to the call of the eigenvalue problem. So the operator is operator del squared has eigenvalues plus or minus k squared. And based on the specific situation, you can get eigenvalues. So let's take a very simple example involving the heat equation in one dimension. Now I won't do the full details of this. They're there in the notes. I'll just sketch some of the details. But you basically have a warm room in the winter and a cold air in the outside. So what we're going to do is we're going to assume that the temperature of the room and unfortunately here I'm going to use the symbol T for temperature as well. Some people like to use theta so as not to confuse with the time T, but I think it's clear from the context what's time and what's temperature. Now I'm going to assume that you don't really have to assume, you'll end up proving that you have a straight line. So what we're going to do is we're going to assume that this is a state for a long time before you open the window. So the air conditioner has been going or the heater has been going and the air outside has not cooled down appreciably beyond a certain temperature. So this situation has been around for a very long time. So we can use the fact that the Laplace's equation is satisfied. Since this is all 1D, the Laplace equation is just d2 phi over dx squared equal to 0. Now the solution to that is phi equals ax plus b. Because when you take the first derivative, I get d phi by dx equals a, and the second derivative I get 0. So the straight line is the only solution. And the other piece of information I get from the fact that this is 0 is that the temperature is also constant. So the full solution, because the temperature is also constant, because 1 over alpha squared t prime over t, which is equal to this, is also 0, which means that t prime must be equal to 0 or t equals constant. So the full solution phi is some other constant a tilde x plus b tilde, okay, where a tilde is this constant times a and b tilde is this constant times b. So we have the initial conditions completely determined. Now when you open the window at time 0, then the left side is at a certain temperature and the right side is at a certain temperature, and you can extrapolate the two. You already know that the linear behavior should be found, but since the left side is at TL and the right side is at TR, you can immediately either guess or work out the full temperature profile at time 0, and that's going to be the following. It's just a straight line fitted between those 2 points. Now, after a very long time, we expect, when you open the window, we expect that, so what you're doing is on a very warm inside and it's very cold outside and you want to get some fresh air, so you open the window and you leave it, you forget about it and you leave it open for a long time. Then eventually the temperature of the inside will also slowly go down and become that of the outside. Now how it goes down is goes down like that, okay, and eventually it becomes the same as temperature outside. So what we want to do is, you want to say at T equals infinity, the temperature at any point x after a long time must be TR. So you can actually do the following. You can impose a new set of boundary conditions, and this is very important, and we'll call these boundary conditions psi. Psi of x comma t is the asymptotic infinity boundary conditions plus the conditions at any given time. If you do that, you get TR plus phi of x comma t. Now the advantage with doing this is that with respect to these new coordinate psi of 0t, which is TR plus phi of 0t, will just be 0 because the temperature at T is TR. So this is going to be TR equals TR plus phi of 0t, which means with respect to these boundaries conditions, you get the conditions phi of 0t equals 0. And now, because we have invented this, let's see what happens at LT. At LT you also have TR, which is TR plus phi of L comma t, and if you cancel out the TRs on both sides, you'll find that phi of L comma t is also 0. So in this way, by adding simply the final asymptotic infinity boundary conditions and manufacturing a psi coordinate, we have actually got homogeneous boundary conditions. That's what they are called. So you can always convert a non-homogeneous boundary condition problem to a homogeneous boundary condition problem by adding the asymptotic infinity. So the heat equation remains the same though, because when you take this variable psi and take the second derivative of it, psi xx equal to 1 over alpha squared psi t, it doesn't really matter whether you're considering the psi variable or the phi variable, because the only difference between the psi variable and the phi variable is you're offsetting it by a constant, and each time you take the derivatives, the constant simply vanishes. So you're still solving, you still end up solving the good old heat equation with respect to the phi variable, equals 1 over alpha squared phi t. Now you do the same separation of variables and you get the Helmholtz equation. The Helmholtz equation this time is rather trivial. You just get phi double prime equals plus k squared phi equals 0. you use the plus k squared for heat and minus k squared for Schrödinger. And for the time coordinate, you just get the same behavior you had for time, for the time part. So it's c e to the minus k squared alpha squared t for the heat equation. And this part, when you solve this, you're going to get sine and cosine as usual. Now at t equals, at x equals 0, the boundary condition is 0. That means you won't get the cosine term, you'll only get the sine term. But when x equals L, the value is also 0, so then you'll get the quantization on the sine, just as you did for the wave equation problem. So Helmholtz equation gets completely tamed and becomes a regular one-dimensional wave equation problem with standing wave type conditions. So I'll get phi will be simply equal to Bn sine of n pi x over L, where L is the thickness of the window, and then the full solution, capital Phi, is just the sum from n equals 1 to infinity, all these bn's sine n pi x over L times e to the, now there you have to put a k sub n, because k is related to the k sub n is just that thing here. K sub n is n pi over L. So we have to use that on the exponent. K sub n squared alpha squared times t. So that's the full solution. And to find these bn's, you proceed as follows. You use the initial conditions. The initial conditions on phi have to be used. Those initial conditions are right here. Phi of x0 is given to be this initial shape. So it's a shape initial condition. So using the shape initial condition, I won't write that function, which is this function. We'll assume that it's just given. That's equal to the integral, it's equal to the sum of n equals 1 to infinity, bn, times sine of n pi x over L at time 0, so this doesn't contribute, and you can find bn's using the usual orthonormality conditions of Fourier analysis. Now once you find all the bn's, you can substitute it back and get the psi function, because remember, psi is our solution. And the details of this is carried out in the notes. But this gives you an idea of how the Helmholtz equation shows up as a small part of the full scheme of solutions.